This is problem number 1218. We're given that the velocity of the train is expressed by the function v of t is equal to 60 minus 60 e to the minus t feet per second. The problem requires that we find the distance, which can be represented by the variable s, and the acceleration, which can be represented by the variable a, by the time the train has traveled 3 seconds. So t equals 3 seconds. The way you want to do this problem is always develop a table expressing the kinematic variables involved in the problem. So we'll usually have time, position, velocity, and acceleration. So we're only given this velocity as a function of time, and what they would like for us to find is what is the position and what is the acceleration at t equals 3. Now, the cue for this problem for you students is that if you ever have a kinematic variable expressed as a function of time, in this instant it happens to be velocity, you're going to end up either differentiating or integrating. In other words, you're going to end up using equations 12.1 through 12.3. So again, the cue is you're given a v of t, so you'll either integrate or differentiate using equations 12.1 through 12.3. So given a velocity function, we can find the position by integrating it, meaning we know that velocity is ds dt. So since v, the expression for v is known, we'll substitute that. So that'll be 60 minus 60 e to the minus t is equal to ds dt. Now we'll bring dt over onto this side, so we'll get 60 minus 60 e to the minus t dt is equal to ds. Now we're in the position to integrate this equation, and we can integrate from 0 to t, and on this side we can integrate from 0 to s. You should note that the integral of e to the at dt is given by e to the at divided by a plus c, where we'll assume c is 0. So in our problem, this a variable is actually -1. So integrating this will yield 60 t minus 60 e to the minus t. Now we have to divide by that constant. In our case, it's -1, and we'll evaluate it from 0 to t. On the right hand side, that's just simply s minus s naught. So we'll have to evaluate this left side, so that'll be 60t plus, because there's a negative and there's a negative, so it'll turn into positive. So it'll be 60 e to the minus t minus 60 times 0 plus 60 e to the 0 is equal to s minus s naught. We continue to simplify this expression. That'll be 60t plus 60 e to the minus t minus 0 and minus 60 times 1 is equal to s minus s naught. So we can simplify this expression, which then turns out to be 60t plus 60e to the minus t minus 0 minus 60 times 1, which is equal to s minus s naught. The initial position is 0, so we now have an expression for position as a function of time given by the following. Position that the train has when t is equal to 3 seconds. That'll be 60 times 3 plus 60 to the e to the minus 3 seconds minus 60. Now solving for s will then yield 123 feet. And that's the next thing we need to find is now the acceleration. Now, again, since we have the velocity as a function of time, to get acceleration, all we need to do is take the derivative. Right, so we just finished integrating, now we're going to take the derivative of the velocity function. So we take the derivative of the velocity equation to get acceleration. So we're going to take d of 60 minus 60 e to the minus t dt, and that would be in feet per second squared. That'll yield the derivative of 60 dt minus the derivative of 60 e to the minus t dt. Derivative of a constant is 0, so we're just left with 0 minus the derivative of an exponential function times a constant. You should note that derivative of e to the at dt. So derivative of that would be e to the at times the derivative of at dt. Since a is a constant, that would simply be e to the at times a. So in our problem right here, that a is a negative 1, so that would be 60 e to the minus t times a negative 1, which will be 60 e to the minus t. So to evaluate that function at t equals 3 seconds, will then be 60 e to the minus 3, yielding 2.99 feet per second squared. And that's the solution.